This is the video answer key for the Unit I review guide on thermochemistry. So question 1 refers to the lab experiment that Connor did called the Flaming Hot Cheeto Lab. He burns a Dorito with a mass of 4.2 grams underneath a can of water. The can holds 80.5 milliliters of water, and the temperature increases from 22.1 degrees to 33.6 degrees. So the question is, how much energy does the water gain? The first question makes the distinction between energy and temperature. So the equation of Q equals mc delta T solves for energy. Q is energy. So you need to know the mass of the water, because 80.5 milliliters is the same as 80.5 grams of water. That one is easy to change. The C of water is always 4.18 joules per gram times degrees Celsius. And the change in temperature is when the water goes from 22.1 to 33.6. So that change in temperature is 11.5 degrees Celsius. So when you do all of this math together, if you put it all into your calculator, you get 3,869.635 joules. And since all of these numbers over here have 3 significant figures, our answer should have 3 significant figures. So we would round this to 3,870 joules. Which means if the water gained 3,870 joules, that means that the Dorito lost 3,870 joules. This is the first law of thermodynamics. For all of the gain by the surroundings, that means that the system must have lost that energy. So if we are trying to look for energy per gram, that means that you have to take the energy produced by the Dorito and divide it by the mass of the Dorito. So if you do this on a calculator, you would calculate that the energy change is 921 joules per gram. Question 2 is a different type of calorimetry problem. It's where you take a mass of a certain piece of metal and you drop that hot metal into cold water. If you can determine the energy that the water gains, that means you can determine the energy that the metal lost. So a really important step for these kinds of problems is to keep track of the variables for each separate system. So the metal has a mass of 34.8 grams. And we have at least a multiple choice question here. It's probably one of those 3. So the initial temperature, the temperature change relies on the final and the initial. So we know that it is heated up to 100 degrees. And then we keep track of all of the water. So the water has a mass of 50 milliliters, which means that the mass is 50 grams. The C for water is always given, joules per gram times degrees Celsius. And the delta T of water relies on the final and the initial. So the final was 45.0 and the initial was 42.8. So the change in temperature was 2.2 degrees Celsius. So back to the metal. The solution ended at 45, so that's the final temperature of the metal also. So these two things are always going to be equal, the final temperature of the metal and the final temperature of the water, which means you can calculate the change in temperature of the metal to be 55 degrees Celsius. And the only thing we don't know is the specific heat of the metal. So in this case, remember, the specific heat of the metal plus the specific heat of the water has to equal 0. So for the water, if it is, let's do water in blue, is 50 grams times 4.18 times 2.2 degrees Celsius. If you did all of this math on a calculator, you would get the number 459.8 joules. So because we are down to, when we measured to 3 significant figures in all of these places, we would round to the 3rd significant figure. So this has to round based on that, so 460 with a period. This period makes this 0 significant. Okay, so if the water gained 460 joules of energy, that means that the metal lost 460 joules of energy. Okay, and then the last question asks, what is the specific heat of the metal? So now you know that the Q of the metal equals M times C times delta T. So that means that C equals Q divided by M times delta T. And we know the variables for all of those now. So the specific heat is negative 460 joules divided by the mass, 34.8 grams, divided by the change in temperature. And in this case, I neglected to mention that the change in temperature is negative. It's always final minus initial. So this is actually a negative 55. So if you did all of this math together, you would see that C equals 0.24 joules per grams times degrees Celsius. If you click the link that's embedded within the document, it will take you to a data table that shows you the specific heat of a bunch of different metals. And this specific heat is the one for silver. So you can tell that this element is silver. Question 3 deals with using a thermochemical equation to determine the enthalpy change. So in this case, you take ammonium chloride and you dissolve it in water. So we measure the change in temperature. One thing that would be really helpful is if you write the equation. So ammonium chloride is dissolved in water. So it's not technically reacting with it, but when something dissociates, it splits into its ions. So ammonium chloride has ammonium ions and chloride ions. And right now we're just writing the chemical reaction. If we were to write the thermochemical reaction, we would have to put the delta H in, but we'll do that after we figure out what the delta H is. So for water, it asks you to determine the energy lost, which means that's Q. So you need all of these variables for water. The mass of water is the same as its volume, so 40 grams. The C for water is always 4.18 joules per gram times degrees Celsius. Oh, and when it's a liquid, actually. And the change in temperature is the final, 14.3, minus the initial, 23.2. So if you do this math, that's 8.9 degrees Celsius. So Q is the question, how much energy is gained or lost by the water. And if you did all this math in a calculator, 1,488.08. So if you were looking to solve this number, it is based on the rules for significant figures. We have 3 significant figures, so that's negative 1,490 joules. The C asks if the dissociation is endothermic or exothermic. So in this case, we have our system and surroundings. So the surroundings are the water, and the inside is the reaction. The temperature in the water went down, which means that the energy must have gone into the reaction. So this is an endothermic reaction. And we know because the water's temperature went down, which means that the reaction required energy in order to happen. So this is endothermic. And it's because the temperature of the water decreased. So to determine the enthalpy change per mole, we need to determine how many moles do we have. So the question uses 5.35 grams of ammonium chloride. And it asks you to change it into moles. So you need to know that 1 mole has 53.50 grams. So in this case, there are 0.100 moles of ammonium chloride. If it takes 0.100 moles and 1,490 joules are released, if you are trying to figure out energy per mole, so enthalpy per mole, you take the energy divided by the moles. So in this case, 1,490 divided by 0.1 is the same as multiplying by 10. So you end up with 14. This is positive because the ammonium chloride is gaining the energy. The water lost the energy, but this has got to be a positive number. 14,900 joules also known as 14.9 kilojoules per mole. Question 4 asks you to use the heats of formation to determine an enthalpy change that would occur for a reaction. So it asks if propane is burned, so you have propane, and it is burned, so that means it reacts with oxygen, produces carbon dioxide and water. So this is the reaction for the burning of propane. When you balance it, there's 3 carbons, so you'll need 3 carbon dioxides. You have 8 hydrogens, so you'll need 4 waters. And together, 6 oxygens and 4 oxygens is 10. So you'll need 5 molecules of oxygen to balance out the reaction. In the heat of formation, it's really helpful if you list each chemical's enthalpy of formation. So the enthalpy of formation for propane is 103.847. So this is where you're going to find all of those. There's this table. It was linked in the document from Google Classroom. So you click on this link and it will take you to a table that has all of these values. So you'll need this for the test tomorrow. Make sure you have one. Oxygen is just a 0 because it's an element. The other compounds are carbon dioxide. So carbon dioxide has an enthalpy of formation of negative 393.714. Oh, and these are all kilojoules per mole, kilojoule per mole. And then water. So there's different versions of water. The one we're talking about is the liquid version. All right, so the liquid version of water has negative 285.767 kilojoules per mole. So those are the 4 enthalpies you're going to need in order to do this equation, the summation of the heats of formation. So in order to get enough detail, you need to understand that the enthalpy change for the reaction is equal to the sum of the heats of formation of all of the products minus the sum of the enthalpy change for all of the reactants. So in this case, your products are 3 carbon dioxides and 4 waters. So we have to take 3 times the carbon dioxide, which was negative 393.714. And then we have to add the other enthalpies for the products. So there are 2 molecules of water, and each molecule is negative 285.767. And then you subtract all of the reactants, and there's really only one reactant. It's propane, and there's only one of them, so it's 103.847. So all of the products are negative 1181.142 plus negative 1143, and then minus negative 103.847. From here, you can just add them all up. So the total enthalpy change is negative 2,220.363 kilojoules per mole. So if this is a negative, if this delta H is negative, that means that this energy is produced, which should make sense. When you burn something, energy is released. So you have propane plus 5 oxygens produces carbon dioxide, 3 carbon dioxides, and 4 waters, and the 2,220 kilojoules. So that means for 1 mole of propane, you release 2,220 kilojoules. Continuing with this problem, if you have 1 mole of propane, you release 2,220 kilojoules. You don't have 1 mole though, you have 16 grams. So if you have 16 grams of propane, you have to change it into moles. So 1 mole of propane, if you look up the molar mass, so you use all of the elements, add them together, you should have 44.11 grams. And from here, 1 mole releases 2,220 kilojoules. So you have this problem set up in a way where you can just multiply across the top, divide by the bottom, you end up with 805 kilojoules. In question 5, it asks you to use Hess's law to solve for an unknown reaction. So the unknown reaction is carbon monoxide reacts with nitrogen monoxide to produce carbon dioxide gas and nitrogen gas. So in order to use this reaction, we have to balance it. So on the right side, you have 2 nitrogens, so you're definitely going to need at least 2 nitrogens, which makes you have 3 oxygens, so that doesn't balance. So there's 4 oxygens, and now you have 2 carbons on the right and 2 on the left, and your 4 oxygens on the left and 4 oxygens on the right. So this is the balanced equation that you need to use, but the question says you don't know the enthalpy. So this is what we're solving for. So we do have 2 given reactions that you do know the enthalpy changes for, even if they didn't transfer correctly. 566 kilojoules is released by the first reaction, and 180.6 kilojoules are released by the second reaction. So in this case, we just look at our target reaction up here, and we look at which parts from the givens match which parts from the target. So in the given, this part actually does match the product from the target. So it looks like this is not going to change. The 2 carbons are on the left side, and the 2 carbon dioxides are on the right side. The other thing in the target reaction, though, is nitrogen. And in the second reaction, nitrogen is on the left side. So this reaction is going to switch. So you're going to just switch the sides of the reaction, which means that delta H is going to switch signs. So this becomes 2NO produces N2 plus O2. So now we have produced the N2 to match up here. We have the 2 NOs will match in the reactant side. You have your 2 carbon monoxides to match there. And you have the 2 carbon dioxides to match there. The only things that are left over, so this reaction is done. The only things that are left over is this oxygen on the left side of the arrow and this oxygen on the right side of the arrow. Since they're the same element and the same number, they can cancel. And when you add the 2 reactions together, you take your 2 carbon monoxides from a given A. You take your 2 nitrogen monoxides from reaction B, and that produces the 2 carbon dioxides from reaction A and the nitrogen from reaction B. So since all you did was switch the direction of reaction B, the only thing you have to do to the enthalpies is switch the sign for reaction B. In this case, if you add these 2 enthalpies together, you would end up with a negative 746.6 kilojoules. Because this reaction is negative, that means that the enthalpy term has to go on the product side. Okay, so the reaction is 2 carbon monoxides plus 2 nitrogen monoxides yields 2 carbon dioxides and nitrogen and 746.6 kilojoules. So for 2 moles of carbon monoxide, you will release 746.6 kilojoules of energy. That's it. Good luck on your test on Wednesday. If you have any questions, you can either email me or try to make it into office hours. I'll be available Tuesday morning. I do have a meeting Tuesday afternoon during half of office hours, so feel free to send me an email and set up another time. Good luck.